Okay, I intend to finish the scattering theory today. We will start new topics. Let's just go over what we had done last week. We looked at the hard sphere scattering, and the basic idea was to calculate explicitly the phase shifts and to get some kind of an idea of what these phase shifts are.
I had this one question a couple of nights ago. I was thinking, what I know about wave functions is that they should be single valued, right? So how does a spherical probability function happen?
What do you mean a spherical probability function?
The wave function goes as spherical waves, right? Then spherical waves cannot be single valued.
What do you mean? Why not?
X ekseni üstünde hocam şöyle giden bir wave. These guys are not single valued.
Why not?
At this axis, it has two values.
Those 2 points are at different points.
Yeah, but it's in the same x-axis, right?
No.
This is the spatial axis. This is the potential axis.
No. That is x, the other one is y. X, y, z.
Uzay zamanda öyleydi, tamam, doğru.
Nasıl potansiyel?
Yok, ben potential in a box gibi düşündüm onu, niyeyse.
Anyway, you can forget about this question. Other questions? Okay, so if you go back to last lecture, we were looking at the hard sphere scattering. It's a problem that we can solve exactly. That's the reason why we study that. And in fact, the radial wave functions just turn out to be spherical Bessel functions. Well, there are 2 of them, J and M. One of them, N diverges at origin, J is finite at origin, but since we are looking at solutions outside this spherical shell, sphere, which contains the origin, we have both solutions, but we have the boundary condition that it has to be 0 right at the surface of the shell, which allowed us to determine, well, where do I have it? Which allows us to determine what the phase shifts are. And as a specific example, we looked at what is the phase shift at L is equal to 0. And, okay, where do I have that plot? If you just look at the radial wave function, the u, which is r times the radial part of the wave function, the phase shift is actually just shifts the wave forward or backward. That's the only thing that the scattering potential can do. In the hard sphere case, the wave is 0 within the shell, so as a whole it is shifted. But in a more realistic potential, where in a certain region it is finite, well, the wave is non-zero within the shell, but the wavelength will change. So outside, again, the only effect you will see is the outside wave will shift out or in. For whether it is, if you have an attractive potential, basically the wave is shifted in, a repulsive potential pushes the wave out. But this in and out, you should also be a bit careful, because if you just pull the wave function in by something close to the wavelength, the total effect will be as if it is just pushed out slightly. And then we looked at the several limits. In the low energy limit, one of the important things that we showed was we have only the small angular momentum contributing. The dominant contribution comes from L is equal to 0. Well, okay, this is what the quantum mechanics tells us, but that is also what we expect from classical physics. If you have low energy, that means low momentum. And remember, angular momentum is momentum times the distance. And for scattered particles, that distance can be at most the size of the shell. So that's a small number also. A small momentum times a small distance, the angular momentum will be small. And we found out that the total scattering cross-section was 4 pi r squared. That's not a big surprise because we are in the domain of wave mechanics. They are not we cannot treat it as point objects. So this total cross-section, it's not a big surprise that the total cross-section turns out to be larger than the physical cross-section of the object. Now, the other extreme was kind of a larger surprise. We looked at high energy limit. Of course, for that we use what's called the iconal approximation, or it's a semi-classical approach where you use the classical action to define your wave function, psi plus, and using that classical action, that wave function defined in terms of the classical action, you can approximate the scattering amplitude. Now, this one over here. And in this case also, when we calculate we could calculate these are just our phase shifts. We can calculate all the phase shifts. Again, here, if you just look at in this expression, if B is large, if B is larger than the range of the potential, then V will be 0, whatever the value of Z prime is. Well, this is squared. Whatever the value of Z double prime is, V will be 0, so the phase shift is 0. Again, this is not a big surprise, considering the classical limit. In the classical limit, if the largest angular momentum you will get, now, in the classical limit, if B is larger than R, that impact parameter is larger than the size of the potential, well, the particle just doesn't hit your potential, so it's not scattered. And we went ahead and calculated the scattering cross-section. The total cross-section this time also turned out to be twice the physical cross-section. Now, remember the correspondence principle from quantum mechanics. It says that for large quantum numbers, we have to recover the classical result. So this is large energy is large quantum numbers in this case. We don't recover the classical result. But then we said, okay, there is this shadow. We interpret this factor 2 by, you see, if you are treating these as particles, looking at it as a wave, some of that wave has to scatter into the shadow to destructively interfere with the incident wave. So that is why, in fact, when we calculate this total cross-section, we have this additional factor 2. If we only look what we identify as the reflected wave, this part, the total cross-section does turn out to be the physical cross-section. So again, our physical classical limit intuition still holds, but we have to be a bit careful about that. Now, any questions up to here? Okay, as I said, I don't intend to continue too much with the scattering theory. I feel that I already lost most of you about all these scattering discussions. But there is one thing I don't want to pass without mentioning: the bound states. And resonances. Okay, we wrote down this psi plus wave function, which was 1 over L. If you use the box normalization, it's 1 over L to the 3 over 2. In the infinite Dirac delta normalization, that is 2 pi to the 3 halves. I don't really care about that factor at this moment. This is k dot r plus some scattering amplitude e to power I kr over r. This is we derived in the limit that r is much larger than the range of our potential. So we are looking at the problem from a faraway distance where the potential is 0. In fact, this is a solution of the free Schrödinger equation. Now, let's just consider a potential, an attractive potential. Well, such an attractive potential might also have bound states. Now, if we have a bound state of this potential, if again we looked at R larger than the range of the potential will be 0. The energy will be negative. So I can write E as, let's say, minus h bar squared, kappa squared over 2m. The Schrödinger equation will take this form. This will be the form of our Schrödinger equation. And if you look at the solution of this equation will be, since we are looking at normalizable solutions, the wave function has to go to 0 at infinity. So the solution of this equation, which goes to 0 at infinity, has this form. Multiply. This is the radial part, let's say. You can also have other parts. So whatever your bound state is, whatever your potential is, in fact, outside the potential, your wave function has to have this form. Now let's compare it with this one. Well, they look similar. If they will be identical, in fact, if I make the identification that k is equal to I times kappa, and f of theta diverges. Remember, f of, well, let me write it in this form, f k prime k. Now, why will they have this form? Remember, we have to normalize the wave functions properly, which if f diverges, it only means that with proper normalization, the first term will be absent. You see, if I properly normalize it, I should divide this by 1 plus f squared with some such function. In the limit f goes to infinity, f over 1 plus f squared is 1 over, this is 0. So divergent f isn't really a problem. It only tells me that if in such a limit, the only term that appears in my psi plus is the second one, not the first one doesn't appear. Well, that is what I want. There's no incoming plane wave. Well, of course, this is kind of a weird transformation. Remember, k is momentum. And we take an imaginary momentum and find bound states. You see, this problem, this solution we obtain by the condition that, okay, we want a solution which has an incoming plane wave plus an outgoing spherical wave. Then k would be positive, etc. But if I make this transformation, and if f theta diverges for certain values of kappa, that is my bound state. Which is, well, in a sense, this is called analytical continuation.
May I ask you a question, maybe a bad one? Does this solution or what we found in here have any relation with vertex bound state, vertex operators or something? Any relation?
No. Well, of course, if you manage to calculate some scattering process in some field theory, if you can We will come in a moment. If you can sum up some infinite series, infinite terms in that expansion, and determine the exact scattering amplitude that is exact in some sense, in that case you can obtain poles, and those poles will give you the bound states of those scattered particles.
I've lost a lot of things.
Okay.
Can you go up a bit? This is the incoming particle's energy, right?
Which one? This one.
E equals minus h bar squared kappa square over 2m.
Well, I'm looking for a solution of this equation.
Yeah, but I'm also searching bound states, and there should also be a potential. So there's the potential in the second equation.
Yeah, you see, here is the potential, but then I'm looking at what will be the shape of my wave function outside the range of my potential. You see, remember the solution of a Dirac delta potential. Okay, what did we do? We looked at the solutions in which the potential is 0, and then matched them somehow. Well, this is exactly what I'm doing over here. Or remember how you solve the potential well problem, a finite potential well. You divide it in different regions where the potential is 0, regions where the potential is non-zero. You solve them separately and then match them. So here I don't really care about the exact solution. What I'm saying is, let me just look at my Schrödinger equation in the regions where the potential is 0. So that's why I have this one. In those regions where the potential is 0, well, this is my Schrödinger equation.
I'm trying to find the incoming wave becomes a bound state.
No, I mean, forget about the incoming wave in this problem. Now, in this case, I'm just looking at, I have a potential. Forget about scattering theory for the time being. I have a potential. I'm asking myself the question, what are the bound states of this potential? And then I say, okay, let me first solve my wave function in regions where the potential is 0. These are my solutions. So whatever the potential is in my region, outside that region, my wave function has to have this form. Well, if you like, there's also the YLM parts. But my wave function has to have this form outside my potential region. Then now I compare this with my scattering problem. So this is my scattering problem. In that problem, I also did this basically the same thing. This is the solution of my psi plus outside the region of my potential, which is an incoming wave plus an incoming plane wave and outgoing spherical wave. Then I'm basically doing a mathematical trick. I just compare these two. There are two differences. One is when you looked at the bound state solution, it's an exponentially decaying solution, whereas the scattering solution is an exponentially oscillating solution, radially outward wave. But I can transform one to the other by this identification. If I assume the k vector of the scattering amplitude to be purely imaginary, then it becomes a decaying solution. So that, if I make this identification, let's say, then at least those terms, the spherical wave part and the bound state solution, they look similar. But still there is the problem of this incoming plane wave. In my bound state solution, I don't have an incoming plane wave. So I have to get rid of them. If I would like to somehow relate these two solutions, I have to also get rid of that e to power ikr term. How can I do that? Well, if f goes to infinity, fk prime k, that basically tells me that the plane wave solution is not actually there. So that is my second requirement. F diverges. So if I look at my scattering solution, if I can somehow calculate it analytically, of course in that solution I assume k to be a real number, but once I obtain an analytical function, I can imagine an analytical function of k, or real k, I can imagine it to be a function of a complex k. Then if it has a pole when k is purely imaginary, that is where I have a bound state. I will make an example of this, an example solution. In fact, let's look at our Dirac delta potential. It's a one-dimensional. I will look at it in a one-dimensional case, which we have somewhat discussed how to solve it in class. It was a part of a question in the exam, and now let's solve it using a different method. Now, psi plus satisfy this equation. This is the equation it's satisfied. Now, this solution, this e to power I k r over r, this spherical wave solution, that is valid in 3 dimensions. In 1 dimension, it will look different. So I would first convert it to an integral equation for the wave function. Let me define the wave function in this form. So psi plus of x is xk plus x1 over e minus h0 plus I epsilon v psi plus. I insert the identity. I'm basically repeating what we had already done before in the 1-dimensional case. So this will be e to power I k x divided by square root of 2 pi. I'm using Dirac delta normalization. And plus dx prime x1 over e minus h0 plus I epsilon x prime v x prime psi plus x prime. This is my psi plus wave function in coordinate space. Now I need to calculate this one in order to proceed further. This will be equal to dk. I'm just inserting an identity. x1 over e minus h0 plus I epsilon k x prime. I know how h0 acts on k. Plus I epsilon h power I k x minus I k x prime divided by 2 pi. K goes from minus infinity to infinity. Again, k is also 1-dimensional. So let me write this as 2m over h bar squared, 1 over 2 pi from minus infinity to infinity, dk 1 over 2m over h bar squared e minus k squared plus I epsilon e to power I k x minus x prime. Well, the epsilon in the last line and the epsilon in the previous line, they are slightly different, up to a positive constant, but the only thing I care about epsilon is that it is positive and very small. Now, we have already discussed how to evaluate these integrals. We just close, if x minus x prime is larger than 0 in the complex k plane, I am evaluating this along the real k line. It has 2 poles, one here and the other one over here in the complex plane. Now, if x minus x prime is positive, I have to close my contour from the above This is when kx minus x prime is positive. So this pole is inside my contour. If x minus x prime is negative, I have to close the contour from the lower axis so that there is no contribution from that arc. And now it's a loop integral. I can use Cauchy integral formula. So this just gives me 2m over h bar squared, 2 pi I divided by 2 pi. Now the residue of this integral is 1 over 2k. And the result will be ik x minus x prime. You can fill in the blanks. So this will be the result of that integral. Now let me do some simplifications. This will be 2mi over h bar squared. Now 2's also cancel. H bar squared k e to power I k x minus x prime. So I can just go back to my equation here. Psi plus of x will be e to power I k x divided by square root of 2 pi. And then I have an x prime integral. This term, mi over h bar squared k e to power I k x minus x prime. My potential is minus lambda Dirac delta x prime psi plus of x prime, which becomes divided by square root of 2 pi minus or plus mi over h bar squared k e to power I k x, absolute value of x, minus lambda psi plus of 0. Which, by the way, has this form. Since it's a one-dimensional wave, the amplitude doesn't get suppressed at large distance, so it's not spreading. That's why we don't have the 1 over r factor in one dimension. And the first wave is an incoming plane wave. The second term is just, you can imagine it as two plane waves moving away from my potential. For its positive, it is a right moving wave. For its negative, it's a left moving wave. So that is my scattered term, and f is my scattering amplitude. So I need to determine f. So this is the equation satisfied by psi plus.
May I ask a question?
Sure.
If you were to expand psi plus in terms of this PL cosine thetas that we do before.
Okay.
So if you do that, since psi plus at 0, PL cosine theta will give 1, right? Then we can find a solution for all n, right? Because we have in the formula.
Well, I wouldn't use this. I mean, you see, that expansion is valid in 3 dimensions. So, I mean, in 3 dimensions, you can define an angular momentum.
Yeah.
You can talk about theta, PLs, etc. But it's just a one-dimensional problem. Now, let's continue along that line. That equation should be satisfied at all values of x, but keep in mind that that's an exact equation. I didn't make any approximations in this problem because my potential is a Dirac delta potential, so the integral I can trivially evaluate. And this, well, that is basically my solution. You see, psi plus 0 is some number, so I know the x dependence. I can even determine what psi plus of 0 is. just set x is equal to 0 on both left and the right hand side. So that equation tells me psi plus of 0 should be equal to 1 over square root of 2 pi plus mi over h bar squared k times minus lambda psi plus of 0. So psi plus of 0 is actually 1 over square root of 2 pi divided by 1 plus mi lambda over h bar squared k. This is my psi plus of 0. So what is f? If we just compare these two equations, f is just the ratio of those two terms. Minus lambda mi divided by h bar squared k times square root of 2 pi psi plus of 0. This is what f is. I'm just comparing these two equations. Well, I now know what psi plus of 0 is, so I can calculate f. Minus lambda mi divided by h bar squared k plus mi lambda. There's a minus sign over here. Well, that tells me that I have a pole. As a function of k, at k is equal to mi lambda over h bar squared. Corresponding energy remember, the energy of this particle is h bar squared k squared over 2m. So this is h bar squared over 2m times minus m squared lambda squared divided by h bar to the 4 minus m lambda squared over 2 h bar squared. This is the bound state energy. Yes. Now the Dirac delta problem has a single pole, and this is the pole. It has a single bound state, and this is the energy of the bound state. And we also have the wave function of the bound state also. This is the wave function of our bound state.
Last question. Now we have a bound state at infinity. We have a pole at infinity. Well,
What do you mean? Why do you think we have a pole at infinity?
Because to do all of this, we assume that R is much, much bigger than R. In the position space.
You see, in this problem, I didn't make any assumption. You see, this is the
But the form of the solution.
no, this is the exact psi plus. This is the integral equation satisfied by psi plus. And I can evaluate this matrix element exactly. No approximations needed. But once I have that exactly, well, this is my potential. Since the potential is a Dirac delta, I can evaluate that integral. Otherwise, as you said, I had to make the assumption that I am away from the potential and then expand this term in this small parameter and then do all the rest. But I'm not making any approximation in this case. If you want to do that approximation, what is the range of this potential?
This potential?
Yes. 0. Well, the range of this potential is 0. It's a Dirac delta potential. So any distance is infinitely far away from 0 relative to this one. So this form, in a sense, you are right. This form is valid for any potential at a sufficiently large distance. But in this case, my solution already has that form at any x. Now that also makes sense because any distance compared to 0 distance is infinitely large.
Define the specific energy for the bound state. How do we know? Okay. Do we have any other solution which admits only specific value for the energy for the bound state?
What do you
Or
mean?
can we have different energy values for bound states? Do I have a unique bound state? In this case, yes.
In this case, yes. In general, no.
And can we say a general thing about the sign of the energy of those states?
Well, it depends on your potential, you see. At least within this approach, we had a very simple scattering amplitude. Let's say that in some other problem, scattering problem, I don't know what potential it will correspond to, but let's say that your scattering amplitude in a different problem will be proportional to 1 over sine hyperbolic k times some parameter a. If we make the same things, if you identify k with I times kappa, this sine hyperbolic becomes ordinary sine. So now, if you have such a scattering amplitude, now you have infinitely many bound states. You see, this approach gives you all the bound states. It's not a big surprise that the scattering amplitude, the poles of the scattering amplitude gives you the energies. Let's go back to our initial definition of psi plus. You see, this is valid whatever potential you have. But this I can also write as plus sum over all the eigenstates. Well, if you like, all the energy eigenstates, sum over integral. And 1 over e minus h0 plus I epsilon v psi plus or 1 over e minus en Yeah, I want the full thing. Sorry, I don't want this one. I want the full solution. Or not this one, sorry. Let me go to T. Do you remember what the T was? T was V plus V 1 over E minus H0 plus I epsilon T. You can go ahead and try to solve for T. Find a formal solution. T will turn out to be 1 over E minus H. Guys, just move this term to the right-hand side, do the simplifications as if they are just ordinary numbers, and this is what you will get. H is H0 plus V. And remember, scattering amplitude, we defined it as K prime T K. Now let me introduce complete eigenstates. This will be K prime, T is 1 over E minus H0, and K. And 1 over E, and remember E is H bar squared. No, let me just keep it as E. E and now, the scattering amplitude is a function of the energy. It does have poles when E is equal to E and for some n. Now, bound states are when the energy is less than 0. So if there is a bound state, its energy will, why should its energy be less than 0, by the way?
I was asking that.
I'm always saying that the energy will be less than 0, but why should it be less than 0?
It's not because of tumbling back.
No.
Because that's the definition of a bound state. We have to give energy to make it a free state.
No, not necessarily, but almost on the right track. You see, a bound state is when a particle cannot go to infinity. So the energy of the bound state should be less than the energy of the potential, less than the potential at infinity. If the total energy is less than the potential at infinity, then it's a bound state.
But you direct out the potential, the bound state goes to infinity.
What do you mean? The energy, the bound state, the wave function goes to 0 at infinity. The probability of observing it at infinity is 0.
No, but what you mean is that the state should be confined in a region in space. In order to be
Now,
balanced.
what you mean by a confined in a region is kind of problematic when you have tails. You see, if your solution goes to 0 exponentially, then we say that it is already confined in a region. My solution, well, the earlier solution we discussed, it goes to 0 exponentially fast. So that is already 0 at infinity.
Okay, so in order to have a bound state, our wave function should confine in some region,
It should be localized in a region.
localized in a region, and this implies a negative energy for that bound state.
Remember, okay, I would like to underline that I am avoiding to use negative energy in my definition of the bound state. What I'm saying is if we have a bound state, it basically means that the particle cannot really go to infinity. It has to decay. The wave function should decay exponentially in the worst case. But that means the total energy of my particle should be less than the potential energy at infinity. Now, in general, not all the time, but quite often, the potential energy at infinity is defined to be 0. If the potential energy at infinity is defined to be zero, a bound state means negative energy. Because in certain problems, it turns out that the potential energy at infinity turns to be infinite.
Simple harmonic oscillator.
Simple harmonic oscillator is an example. Quantum chromodynamics is an example.
Sorry, what's the first one you said?
Simple harmonic
Simple
oscillator.
oscillator.
So the
for asymptotically free potentials,
if you define the potential at infinity to be zero,
okay.
you can define the potential at infinity to be, I don't know, 5 joules if you like. In that case, not being negative is not a criteria. Being less than 5 joules is the criteria.
May I ask a question on
Sure.
on this? So we basically found F, right? For this solution, we found F. But so maybe we don't think any of this, and we solve F like we used to, not with the imaginary momentum. And after we find F, F is not a physical thing, but F squared is the physical. So if we just find F and then analytically continue, can we capture the, yes. So in this region, let's say, F is analytic, no problem. But when we analytically continue to complex plane, there might be some meromorphic properties like some poles and etc. So if we do that, can we capture the bound states already by just finding everything and then analytically continuing F? For this case, maybe, I don't know, but for the sine case, let's say, in some solution, we might find something that is 1 over 2k sine QA, let's say, and Q, if we analytically continue Q, and find something, and is that okay?
The problem is you cannot measure F for all the values. Experimentally, you will just choose certain parameter regions. Those parameters can be the kinematical parameters, and you will measure F within that kinematical region. So what is done sometimes is you assume a reasonable form for F, an analytical form, you use all the constraints that you would like to have. And then that reasonable form will have some free parameters, and you fit those free parameters to the available experimental data. Then you continue to the complex K-plane and see what it tries to tell you.
I have a follow-up question. For the simple harmonic oscillator case, we can safely say that all the states are bounded, right?
Okay.
Is it true if I say, let's say, I have a potential that diverges at infinity, and since any other energy would be less than that, in those potentials, any state is bounded?
Okay.
Is it true?
Yeah, I would say so.
Okay.
I mean, if you follow the time evolution, your state will always be within a finite region.
But this is also true in the classical momentum. I mean, classically, if I have any potential that diverges,
Yeah, the particle will be always within a finite region.
I understood something from my research.
Okay. Happy to hear that. Now, any other questions? That is the definition of a physical system. The potential is bounded from below.
Yani bir tarafı eksi sonsuza doğru diverge, biri artı sonsuza diverge ediyor.
That's not a physical system.
Yeah.
In order to have a quantum system, you have to have a vacuum. And
Even in the classical case, the potential should have a minimum if you would like to have a stable system.
the second derivative of the potential should be.
Okay, so how many of you were working on something related to particle physics?
We count?
Hmm?
We count?
Yes, you do count.
For expanded particles, yes.
I mean, you are also looking at resonances in certain cases. You used to. Weren't you interested in Higgs particles?
Yes.
Okay. You have, I'm sure you have seen plots from particle physics experimentalists that look something like this.
You also showed it in the lecture.
Yeah, I'm a particle physicist, so. Why is that peak? You see, here we said that if you have a bound state, it diverges at certain values of the momentum. Well, that's for imaginary momentum, but still it diverges for some values of momentum. Here you have a nice peak. It looks like some kind of an attempt to diverge, but fails. In fact, that is somewhat a divergence. You see, here we had an explicit example where the wave function diverged at a purely imaginary momentum. Sometimes you get systems. In fact, there's an interesting problem in your book. I will not go into the detail, where you have a three-dimensional problem with a potential given by lambda times Dirac delta R minus A. You have a spherical shell. The potential is plus infinite on the shell and zero everywhere else. So in the limit, lambda goes to infinity. Inside the shell and the outside the shell are completely separate. So you can go ahead and calculate the bound states inside the shell. Now, the eigenstates inside the shell, they will have positive energy. If lambda is not infinite, but finite, then you don't have any eigenstates that are localized inside the shell. But you can go ahead this exercise and calculate the scattering amplitude for various values of k and theta, etc. And it turns out that, again, treating k as a possible complex number, this function also has poles. But the poles have this form. Well, let me write for the absolute square. You said that we are measuring the absolute square of this. This has such a behavior. Let me put En, which is 1 over k minus En squared plus gamma squared over 4. I'm just taking the absolute square. Well, if you would plot that function,
We haven't done analytic continuation, right?
No, I haven't done any analytical continuation. As a function of k is a real number. You are just sending some. Well, in this problem, there are no negative energy solutions because potential is positive and potential is never negative. So you cannot have a negative energy solution. You cannot even hope to have a negative energy solution. So all the solutions will be positive. Now, this FL of k will have such a form.
What is gamma? Gamma.
Some number. Now, if you look at this maximum value, En. Now, if 1 over lambda is very small, whatever that means, En are the eigenvalues of bound solutions inside the shell. So you can still somehow measure the, now they are not stable anymore. So if you create a particle inside your sphere in a state that would have been the eigenstate, let's say, it will stay there for some time, but not indefinitely, and hence it's not an eigenstate. But it's approximately an eigenstate. And the energy of that eigenstate, in fact, is this En value. And the width is determined by gamma. And if you ask yourself the question, what is the rate of escaping from the sphere, that is given by gamma. So if n is the, let's say, number of particles inside the shell, 1 over n dn over dt will be given by minus gamma, which can be calculated as a function of lambda. In fact, you see, here, a more general case would be if you would plot your wave, this is your potential, let's say. Now, if this peak was infinitely high, you would get some eigenstates having these energies. If it's not infinitely high, they are not exact eigenstates, but they are approximately eigenstates in the sense that if you create a particle within that state, they will live long without changing. You can still see these particles by, you can measure these particles by doing scattering experiments. Let's say that if this is your scattered particle, in this case, you can just imagine that that particle cannot really penetrate in, there's no corresponding state inside the shell, so there won't be anything interesting there. But if the energy of your incoming particle matches one of these energy eigenstates, you get this enhanced behavior. Well, you can think of it as your wave is kind of trapped within the shell if its wavelength matches the wavelength of a bound state. Now, this is called resonance scattering. Whenever you see some particle physics collision experiments, is that here there's a so-called resonance when the energy of the incoming particles matches the energy of the particle that you have created. But it won't live long, so you don't measure those particles in your detectors. It will live a very short amount of time, but still long compared to the characteristic time scale of your whatever dynamics. It will live long, not long enough to reach your detector, so you won't see it in your detector, but you will see such peaks in your scattering cross-sections, which will tell you that you are actually creating some particles there. Okay, so any questions? If not, let's give a 10-minute break and then we will continue.